We will see in this tutorial how to use the heliciel software to model a hull, and know the performance of this airship hull. We will start by using the File menu to load a new project template. Here, an airship. So here is the loaded model. We will look at its 3D representation in the Prototype tab, by selecting the graphic zone, and by turning the wheel of the mouse. We will move closer or move back our model. By selecting the Rotate tool, we can rotate. If we start from the end of the screen, we rotate horizontally. Therefore, we will be able to see the 3D modeling of our hull. So, we already see that our hull is represented in the form of a half hull. We are going to use here the calculation method for the wings to estimate the performance of a hull. Considering that an airship hull is a very short wing. Here we have the wing root, and here the wing tip. A diagram in plan view shows the distribution of the elements of our form of airship. Our hull is divided into different elements, which allow us to sculpt our hull. We are going to enlarge our wing, therefore our dirigible width, to see the different elements distinctly, and to understand how the geometry is handled. We are going to go to the Geometry tab, and we are going to set the dimensions of our half hull. There are three primordial dimensions: the depth, the length at the base, and the length at the end. These three dimensions will allow us to determine the overall shape of our hull. The hull depth corresponds to the distance between the center of the hull, which is here, and the end of the hull. It is the dimension in the direction of the y-axis. So the depth of the hull corresponds to the distance between this element at the base and the tip of the wing. This wing is very short. The distance between the base and the tip changes here. We will show how this parameter modifies our shape. We will add a 0. So multiply by 10 the length of our wing. And we will rebuild a 3D model with this new dimension of depth, and we see that our airship hull looks more like a wing. We are now going to see how to modify the length of our hull. And how to configure the evolution of these lengths along this y-axis. So we go back to the Geometry tab, and we will use these two parameters, basic length and bottom length. So basic length mean length at the base. So here at the base of our half hull, which represents the central part of the overall hull, So the base length is given by this field. And the end length is given by this field. The lengths of intermediate elements are set with this slider. We can also apply a linear distribution. Here we will linearize to see an example. We reconstruct the 3D model to see the shape. So here we see that our wing, it has become triangular, and that the distribution of shapes is linear between the foot and the tip of our wing. If we want a more rounded wing, we use the slider here to give curves to our distribution. So this parameter being sensitive, we have a very slight variation, which is possible thanks to these two buttons, more or less. We therefore see the distribution of the strings, which increases or decreases according to this parameter. Here, we have the polynomial which makes it possible to calculate the exact dimensions along the strings. We see the equation evolving. We will increase the curvature and rebuild the hull with the current parameters. We see that the shape has become a little more domed. Now that we have mastered the geometry parameters, we are going to return to a shape which corresponds more to a half hull of an airship, that is to say, a much shorter wing. We go to the Geometry tab, and we will reduce this depth parameter and rebuild a 3D model corresponding more to our specifications, which is an airship hull. In this half hull, we see that the distribution of the ropes gives a fairly pointed object. We want a more rounded front end. Here it would be the center and front of the hull. Here the edge of the half hull. And here the back of our half hull. We're going to round it off a bit more. We switch to the Geometry tab and increase the curvature of our shape. We can use the slider to go faster. We rebuild. And we see our form which becomes a little more curved. If the curvature is too exaggerated, we could obtain a length in the center of the hull less than the lengths of the following elements. This would not be very realistic. So do not exaggerate the curvature. So, in the diagram here, this point should not be lower than this point here. We see here our distribution, and we monitor that this point is always higher. We can still increase. There, we will arrive almost at a straight edge. In this part there are the first element. There we have an almost straight edge in the first element. We will rebuild. And check our form. Here, we can still give the curve. So there, our edge exceeded. So voila, our edge is almost straight on the first element. We could have a hull that is a little wider at the end. So here, we are going to play on the end parameter and slightly increase the end length. We rebuild. We see a hull, determined by the wingtip profile, which has been increased. So that's it for the manipulation of geometry data. And let's see how to apply our little specifications, which here is a 22-meter airship. In a fluid current of 22 meters per second. So we go to the geometry. Enter the length between this point and the end point. In this field there, we will enter 22 meters. In millimeters, we enter 22,000. At the end, we enter 1 millimeter. And we will also determine the depth. So for a hull of 22 meters long, we will say that it is 4 meters wide in half hull, which will give us a total hull width of 8 meters. We always linearize between two changes of dimensions, and we are going to increase the curvature until this point comes tangent with the first point to have a hull with a very straight edge. And we will rebuild with these new parameters. 22,000 at the foot, and we enter 100 millimeters at the end. Rebuild. Here is a form corresponding to our specifications of 22 meters. We will now modify the fluid velocity for this project. In the project data, at the operating point, we will enter 22 meters a second. And we're going to start rebuilding the hull with current settings. So we have in the results area below the performance of this hull that we have just modeled according to this speed of 22 meters per second. And from the geometry that we have here, the performances are therefore for a half hull. They will simply be multiplied by 2 to have the performance of the entire hull. We can also go to the Messages tab, see the performance for a global hull. We want to have a lift, so a lifted mass, here. At this speed there, we have a lift of 551 kilos. In our specifications, we are asked for a lift of 300 kilos. We are above. On the other hand here, we wanted 600 cubic meters. Let's see the volumes in the info pane. In the details, we select for example element 1. And therefore in hull, we will see the volume of the element. Here the volume of the element is 51 cubic meters. The volume of the second element is 46 cubic meters. We add all the elements to obtain the overall volume, 146 cubic meters. This for the half hull. Multiplies by 2, so we get 292 cubic meters. Our specifications specified a volume of 600 cubic meters. So we will have to increase certain parameters. We can increase the crown or the width at the end. Another rating we might want to increase is the thickness of our airship. Here, this thickness given by the selected shape, we could select a more rounded, more spherical shape. In order to increase the volume, this is the option we are going to choose in this tutorial, to show how to modify this shape. We have so far only changed the dimensions of the shape, but we have never changed the shape. So let's see how to use the database to create shapes. In the Geometry tab, we go to the Profile Law tab. To select the profile of our airship, we click on Choose a Profile. This opens the database and allows us to access the different forms available. Here we have a thicker shape, which could correspond to our need. We click on Apply Default Profile. So, our prototype has been rebuilt with this new wider shape. And the volumes have therefore changed. We can redo the addition of the volumes here, 77 for the first part. Second part 70. Third part 50. Fourth part 25. And fifth part 6 cubic meters. This gives us a total of 228 cubic meters, which we will multiply by 2 for the entire hull, which gives us 457 cubic meters. We have therefore considerably increased our overall volume by changing the shape of our hull. We are going to keep this shape and slightly modify the distribution of the profiles to increase the volume. So we go back to the Geometry tab. We will slightly increase the length of the end profile and rebuild. Now let's see how our volumes have evolved. We get a total of 229 cubic meters multiplied by 2 equals 458. That's it. We can further increase the thickness of this profile. And we will take the opportunity to see how to create a profile by transforming an existing profile. So we select Profile here. We will create and modify the profile. Let's have a plotting window, which we are going to open. Here we are going to slightly increase the thickness of the shape of this profile, make it bigger this being done, we carry out a paneling to redistribute the points. We apply and close. We must now calculate the performance of this new profile before saving it in our database. This profile performance calculation takes some time. It takes about 5 to 10 minutes of software work to calculate and save the performance of this profile that we have just created. So we click on Automatic Polar Calculation. OK, we will name our profile before launching the calculation. And we will call it Airship 1. We will save and launch the performance calculation of this new profile. This performance calculation drives a digital wind tunnel, which is X-foil, which will calculate the performance at different Reynolds numbers of the profile shape that we have determined here. We are going to let the software work and resume this tutorial when the calculation is finished. After 15 minutes of calculation, the performances at Reynolds numbers from 1000 to 5 million at angles of attack from 0 to 360 degrees were calculated and recorded. This calculation procedure may seem a little long, but it has the advantage of being executed only once during the creation of the profile, and all the performances are saved in the database, which speeds up greatly the models using this profile. So, at the end of the calculation, we get a message that tells us that the polars have been calculated and saved. We can now select in the Search tab in the list of different profiles, and we see in this list the Airship Profile 1, which has been added. We are going to show an example of creating a specific database. We are going to select this Airship Profile 1 in the search field and use the search function to create a list of profiles made up of this profile only, and we will create a database with this list only. This will serve us later to export or save this profile there in other databases. And we are going to save this database made up of a single profile for the future if we need to export and share this database with a collaborator.
Voilà. Ceci pour mémoire, pour l'avenir, si on a besoin d'exporter ou de faire profiter à quelqu'un d'autre de cette base de données. D'ailleurs, cette base de données sera téléchargeable sur le site via un lien qu'on va mettre sur cette vidéo. Donc voilà, maintenant que nous avons donc enregistré notre profil,
we will now apply our profile, Airship 1, to our current project. To do this, click on Default Profile.
Clique sur Profil par défaut.
This therefore has the effect of updating our project with this new profile. We will now see how the lift and the center of lift can be viewed and modified. To explain this, we will review the performance of a wing. So we are going to lengthen our half hull like a wing, so that we can better understand how the lift changes.
Comment la portance évolue sur ce système.
And we are rebuilding our wing.
Reconstruisons donc notre aile. Donc, qui est plus longue que notre carène.
The performances of the profiles, which are stored in the database, are calculated by a digital wind tunnel for wing lengths of infinite length.
Pour des longueurs d'aile de longueur infinie. Ceci signifie
This means that we do not include, in the performance of the profile, the vortex phenomena at the wingtip. We will see that these phenomena are important and significantly modify the performance in terms of lift and drag of the profiles, and also of the position of the center of lift. For that, let's go back to our wing here and see the distribution of lift on our system. Here we see the lifts applied to our wing. And the position of application of these lifts. We will also see how the vortices at the tip of the wing modify this lift.
Les tourbillons en bout d'aile modifient cette portance.
We display schematic vectors which show us how the wingtip vortices impact the lift phenomenon.
Les tourbillons en bout d'aile impactent le phénomène de portance.
We hide lift. We see vectors,
on voit des vecteurs,
the rotation of which symbolizes the effects of lift and vortices at the wingtip. There are two axes of rotation of these particle vectors. We have a rotation around the y-axis, which symbolizes the phenomenon of lift which deflects the fluid downwards. The more the particle has a significant rotational movement around the y-axis, the greater the lift in the area of the wing is important. And we also have another rotation around the x-axis, which symbolizes the rotation of the flow resulting from the vortex loss generated by the wingtip vortices. So we see here that close to the center implantation zone, there is little vortex rotation, while at the wingtip, there is more vortex rotation.
En bout d'aile, on a plus de rotation tourbillonnaire. Nous allons voir que cet
We will see that this vortex effect modifies the position of the lift.
De la portance.
Here, we will show again the lifts and their positions.
Et leur position.
We go here in the results, see the position of this lift.
La position de cette portance.
We see here that the center of lift
Nous voyons ici que le
is
centre
given
de
for each
portance est donné pour chaque élément par rapport
with respect to the
à
axis of the blade generator, the y-axis. We see that close to the center, the lift axis is a little further forward.
Que proche du centre, l'axe de portance est un petit peu plus en avant.
And that close to the lift point and a little further back from the y-axis. The precise position is given here, distance from the lift point to the y-axis. We see here 1.9 at the foot and 0.6 in end. This recoil phenomenon is generated by the rotation of the flow predicted by the vortex theory. The greater this phenomenon of rotation of the airflow and is felt far on the wing, the more the overall centers of lift will recede. We are now going to go back to the geometry and set our half-hull length back to 4 meters.
D'aile et la réduire à 4 mètres et recalculer nos profils.
And recalculate our performance.
Et reconstruire notre aile.
We will see how the centers of lift have been modified. We will show them again. We see that the centers of lift have been strongly impacted by the vortices.
Par les tourbillons.
And that the general lift of the half hull is very aft, which will generate a hull which tends to rock and dive. These phenomena are of course to be taken into account
pour
to then manage the
gérer
position of the
ensuite
masses
la
attached
position
to this airship.
des centres de masse accrochés à ce dirigeable. Voyons
We
donc que
therefore
la
see that the phenomenon of lift
est
is strongly impacted by the
fortement
length of
impacté
our wing.
par la longueur de notre aile, de notre dirigeable.
If we
Si
want to
nous
create
voulons
an interesting
créer un
lift
effet
effect with a high
d'importance
ratio, lift divided
intéressant,
by drag,
avec un rendement et une
we will
finesse
therefore have to have a shape
intéressante, il nous
which
faudra
corresponds
donc
more to a
avoir
wing.
une forme qui corresponde au mieux à une aile. C'est-à-dire
We
qu'il va
will
falloir
have to increase
augmenter
the overall
l'allongement
aspect
global de
ratio
notre
of our
dirigeable
airship
pour vraiment créer
to
des phénomènes
create phenomena of
d'importance
lift
qui soient
interesting to exploit.
intéressants à exploiter.
Here, for
Ici,
example,
par exemple,
instead
au
of
lieu d'aller
looking for
chercher du
volume in a
volume
thick form,
dans une forme
it would be
large,
in our
nous aurons
interest
donc
to
tout
create
intérêt
our
d'aller
volume
chercher
in the
notre
length of the
volume
wing,
dans
therefore the overall width
la
of our
longueur,
airship,
donc la
and the
largeur,
closer
on
to
va
wing
dire,
shapes,
globale de
rather
notre
than
dirigeable,
sphere
et de
shapes.
transformer plutôt en une aile que en une sphère.
We
Nous
are
allons
therefore
donc
going
ici
to go back to a model
repasser dans un
with a
modèle
narrower profile and
de
longer
forme
wing.
plus oblong,
And
nous
we
allons
will seek to
chercher
create
à
volume
créer du volume
without
non
thickening
plus
our profile,
en
but therefore
épaississant
lengthening
notre
our wing.
forme, mais en allongeant donc notre aile. Ici, dans la
Here, in the
géométrie, nous allons
geometry,
donc
we will
surtout
therefore work on this
travailler
length
sur ce
parameter
paramètre
to increase the
pour augmenter
volume.
le volume. Voyons
So
donc
we
que
see
notre
that
forme
our
de
airship
dirigeable
shape
prend
takes
une
on a
forme
more
plutôt
lenticular than
lenticulaire, on va
spherical
dire,
shape.
que sphérique.
We will thus
Nous obtenons une
obtain
meilleure
better
performance
performance.
qu'avec une forme sphérique.
In
Alors,
this
les
small
performances en
diagram,
3D,
we have the 2D
dans ce petit
performances
schéma
which
ici, nous avons les
correspond to the
performances en 2D
ratios
qui correspondent
2D
aux
lift
finesses
divided by 2D
théoriques des
drag
éléments en 2D,
of the 2D
et
elements,
ici à la finesse en 3D réalisée en
and here the
impactant
3D
donc
ratios integrating the
les
vortex
pertes ou les
losses.
lors de la construction
During the
matérielle est
construction of the
construite
model,
avec une
the
certaine
hull is built
incidence
with a
qui génère
certain
justement
instance,
l'importance
which precisely
optimum
generates the
et
optimum
la
lift
traînée
and the minimum
minimum
drag for this
pour ce
wing.
type de construction. Le détail des incidences est
The
donné
detail of the
lorsque l'on
instances is
clique
given when you click on the
sur
different profiles
différents
in the
profils
profile diagram,
dans le
which can be
schéma des
enlarged
cordes
to
qui peut être
visualize the instances for each element.
agrandi pour visualiser les différentes incidences pour chaque élément.
Other
D'autres
construction
options de
options make it
construction
possible to
permettent
generate a
de
shape
générer
based on a generatrix
une
placed more
forme
or less in
basée sur
front
une
or behind the
génératrice
profile.
placée plus ou moins en avant ou en arrière du profil.
To
Pour
determine the
sélectionner
placement
donc
of
le
the
placement de la
generatrix,
génératrice, nous pouvons aller dans
we go
Géométrie
to the
bar,
Geometry
options
tab,
avancées de
Advanced Geometry Options tab,
et là nous allons
and there
régler
we are going to adjust generatrix
le
to the position we want.
centre de la génératrice sur la position que nous désirons.
So
Donc
here,
ici, par
for
exemple, on va
example,
construire
we will position the
le même
generatrix
style de coque, mais basé sur une génératrice
close to the leading edge.
Quasiment confondu
By
avec le bord
rebuilding,
d'attaque
we
que nous
therefore see
construisons.
our rebuilt hull,
Et nous voyons donc notre coque reconstruite à
with a
partir d'une
generatrix placed on the leading edge.
placée sur le bord d'attaque.
We can
Pour
take the
effectuer la
opposite
démarche
approach
inverse
and go
et
build
aller
our wings with a
construire
generatrix
sur
aligned with the
génératrice,
trailing
donc
edges.
l'axe Y, aligné sur les bords de fuite. Nous allons faire ça tout de suite.
We do this right away by moving the cursor towards the trailing
Par
edge.
défaut, le logiciel
By
a réglé
default,
sur une
the
génératrice à
software is set to a
50%
generatrix at 50% of the chord.
La
Here is the
reconstruction
reconstruction with a
avec
generatrix
une
placed
génératrice
on the trailing
placée
edges.
sur les bords de fuite.
So here is our
Donc voilà
dirigible
notre
hull
terrain de dirigeable
with a generator
avec
placed
la
on the
génératrice
trailing
placée
edges.
sur les bords de fuite. Voilà, nous
That's
avons fait à peu près le
it. This
tour
is
des
the end of this
différents
tutorial.
paramètres
We
de
have
la
seen the
conception
different
de la
parameters of
carène
airship hull
dirigeable. Il y a
design.
beaucoup
There is a lot
effectivement
to be
à
said
dire et à
and to
voir
be seen
sur les
on the
différents
different
paramètres,
parameters.
mais
A
ça, c'est
detailed
après une
study for
étude
each case
détaillée
of figure
pour
and
chaque
each
cas de
project is
figure et
therefore
chaque projet.
necessary.